3 earthquakes, 24 hours, all of them shallow, all of them in nearly the exact same location off the coast of New Zealand's North Island, and all of them sitting directly above a fault system that scientists have been watching with increasing concern for the past 5 years. The largest was magnitude 5.8. That happened at 8 o'clock this morning, UTC time. The second was magnitude 4.9, just 43 minutes later. The third, magnitude 4.5, came less than an hour after that. Same depth on all three. 10 kilometers, that's shallow. Shallow enough that the energy doesn't dissipate through miles of rock before it reaches the surface. Shallow enough that people feel it. Shallow enough that it matters. The location is what makes this different. These earthquakes aren't happening on some random fault segment in the middle of nowhere. They're happening on top of the Hikurangi subduction zone. And if you don't know what that is, you should, because it's the largest source of earthquake and tsunami hazard in the entire country of New Zealand. And what scientists discovered beneath it in the last 3 years suggests that the way we think about how subduction zones fail might be fundamentally wrong. Before we go any further, if you enjoy what we do here at Project Nightfall Watch, make sure you hit like and subscribe so you don't miss any updates as this story develops. Drop a comment and tell me where you're watching from and whether you've ever felt an earthquake yourself. Because your experience matters. This community is built on people who pay attention when the ground starts moving. Now let's get into it. May 5th, 2026, 8 AMUTC, magnitude 5.8. Location 36.745 degrees south, latitude 177.262 degrees east longitude. That puts it roughly 127 kilometers from Pauanui, on the eastern coast of New Zealand's North Island. The depth, according to initial reports, was 10 kilometers below the seafloor. 43 minutes later, at 8:43 a.m. UTC, another earthquake, magnitude 4.9, location 36.641 degrees south, 177.334 degrees east, approximately 136 kilometers from Hicks Bay, same depth, 10 kilometers. 54 minutes after that, at 9:37 a.m. UTC, a third earthquake, magnitude 4.5, location 36.642 degrees south, 177.242 degrees east, back near Pauanui, same depth again, 10 kilometers. 3 earthquakes in less than 2 hours. All of them in a tight geographic cluster. All of them at the same depth. This is not random. This is not background seismicity. This is a swarm. And swarms, unlike isolated earthquakes, tell you something specific about what's happening beneath the surface. An isolated earthquake is a single failure. Stress builds on a fault over years or decades or centuries. The fault locks. The stress exceeds the strength of the rock. The fault slips. The energy releases in one event. Done. The system resets. A swarm is different. A swarm means something is moving beneath the surface right now. It means fluid is migrating through the crust, or magma is intruding into a new location, or a fault is adjusting to a stress change that hasn't finished propagating yet. Swarms don't reset. They evolve. They migrate. They sometimes accelerate. The location of this swarm is what transforms it from a curiosity into a story that matters. Because these 3 earthquakes didn't happen on just any fault. They happened directly above the plate boundary, where the Pacific Plate is diving westward beneath the Australian Plate. They happened on the Hikurangi subduction zone. The Hikurangi subduction zone is not a fault you hear about often in international news coverage. It doesn't have the name recognition of the San Andreas Fault in California or the Cascadia subduction zone in the Pacific Northwest. It doesn't produce the annual headlines that Yellowstone or Mount Vesuvius generate, but it should, because in terms of pure destructive potential, in terms of the number of people at immediate risk, in terms of what could happen if the wrong segment of this fault decides to slip at the wrong time, Hikurangi belongs in the same conversation as the faults that killed 230,000 people in Sumatra in 2004 and 18,000 people in Japan in 2011. The Hikurangi subduction zone stretches along the entire eastern coast of New Zealand's North Island, from well north of the East Cape down to the northeastern tip of the South Island. It's the boundary where the Pacific Plate, one of the largest tectonic plates on Earth, collides with the Australian Plate and is forced downward into the mantle. This is not a gentle process. The Pacific Plate is moving westward at roughly 6 centimeters per year in the northern section of the subduction zone near Gisborne. In the southern section near Wellington, that rate drops to about 2 to 3 centimeters per year. 6 centimeters per year doesn't sound dramatic. That's about the rate your fingernails grow. But over decades, over centuries, that slow grinding motion accumulates into enormous amounts of stored energy. And when that energy releases, it doesn't release gently. The Hikurangi subduction zone is capable of producing magnitude 8 earthquakes. Scientists know this because they have found geological evidence of at least 10 large subduction earthquakes over the past 7,000 years. Some of those earthquakes were magnitude 8 or larger, and the geological record suggests that the southern section of the subduction zone, the part beneath Wellington and the Wairarapa region, ruptures on average about once every 500 years. The last major earthquake on the southern Hikurangi subduction zone occurred approximately 571 years ago. That's 1455 AD, give or take 25 years. If the average recurrence interval is 500 years, and the last event was 571 years ago, then statistically speaking, the southern section is overdue. But that's not the part of the fault that just produced 3 earthquakes in 24 hours. The swarm that happened this morning is further north, closer to Gisborne and the East Cape. And that section of the subduction zone behaves very differently from the locked southern section. Understanding why it behaves differently is central to understanding what today's earthquake swarm might mean. The northern Hikurangi subduction zone, the section offshore from Gisborne and Hawke's Bay, doesn't appear to be locked. GPS measurements show that it's either creeping steadily or moving in what scientists call slow slip events. These are earthquakes, technically, but they're earthquakes that happen so slowly that you can't feel them. The fault slips, releasing energy equivalent to a magnitude 6 or magnitude 7 earthquake, but it does so over weeks or months instead of seconds. No shaking, no tsunami, just slow, continuous motion measured only by GPS stations detecting millimeter-scale displacements of the land surface. Slow slip events have been recorded on the northern Hikurangi subduction zone regularly since they were first discovered in 2002. They happen roughly every year or two offshore from Gisborne. They happen roughly every 5 years beneath the Kapiti Coast and Manawatu regions further south. These events are not rare, they're normal. They're how this section of the fault releases stress. But here's where the story gets complicated, because while slow slip events release stress, they also transfer stress. When one part of a fault slips, even slowly, it loads the neighboring sections with additional stress. And in 2016, scientists documented something that changed how they think about the relationship between slow slip events and larger damaging earthquakes. In November 2016, the Kaikoura earthquake struck the northeastern South Island of New Zealand, magnitude 7.8. That earthquake was complex. It ruptured multiple faults simultaneously, including sections of the Hikurangi subduction zone. And within hours of the main shock, GPS stations across the lower North Island began detecting slow slip events. The Kaikoura earthquake had triggered slow slip on the Hikurangi subduction zone. The stress from one event propagated northward and set off slow earthquakes hundreds of kilometers away. That observation raised an uncomfortable question. If a large earthquake can trigger slow slip events, can slow slip events trigger large earthquakes? The answer appears to be yes, or at least maybe. The science isn't settled yet, but there are documented cases worldwide where slow slip events preceded large subduction earthquakes. And that possibility that a slow slip event currently happening beneath the northern Hikurangi subduction zone could transfer stress to the locked southern section and trigger a magnitude 8 or larger earthquake is what keeps seismologists focused on this fault system. 3 earthquakes in 24 hours. All of them shallow. All of them clustered in a tight geographic area directly above the Hikurangi subduction zone. Is this the start of a slow slip event? Is this the kind of seismicity that precedes a larger rupture? Or is this just normal background activity on one of the most active plate boundaries on Earth? The answer is that nobody knows yet. The earthquakes are too recent. The data is too limited. The pattern hasn't developed far enough to tell whether this is an anomaly or just noise. But the fact that it's happening at all, in this location, at this depth, means it's worth watching, because the last time the Hikurangi subduction zone produced this kind of clustered shallow seismicity in a short time window, scientists started detecting slow slip motion within days. And if a slow slip event is beginning right now, then the question becomes not whether the fault is moving, but where that movement leads. To understand what 3 shallow earthquakes off the coast of New Zealand might mean, you need to understand the geometry of the system they're sitting on top of. And that geometry is not simple. The Hikurangi subduction zone is not a single fault. It's a vast, sloping surface where 2 tectonic plates meet, and one is forced beneath the other. Imagine a ramp descending from the seafloor down into the Earth's mantle. The shallow end of that ramp is near the Hikurangi Trough, a deep trench in the ocean floor about 30 to 50 kilometers offshore from the East Cape. The deep end of that ramp extends hundreds of kilometers westward beneath the North Island, eventually reaching depths of 200 kilometers or more. The Pacific Plate is being forced down this ramp, westward and downward, at a rate that varies depending on location. In the northern section near Gisborne, the convergence rate is about 6 centimeters per year. In the southern section near Wellington, it drops to 2 to 3 centimeters per year. That difference in convergence rate is one of the reasons the 2 sections of the subduction zone behave so differently. The depth of the plate boundary matters enormously. At shallow depths, close to the trench, the temperatures and pressures are relatively low, the rocks are cold, the fault is brittle. When stress exceeds the strength of the rock, the fault fails suddenly, producing sharp, violent earthquakes. This is the zone where tsunami-generating earthquakes happen, because when the shallow part of the fault ruptures, it can displace the entire water column above it, sending waves radiating outward at speeds of 700 kilometers per hour. At deeper depths, beneath the North Island itself, the temperatures increase, the rocks become more ductile, the fault behavior changes. Instead of failing suddenly in large earthquakes, the fault can slip more gradually, producing slow slip events or steady creep. This is the zone where the northern Hikurangi subduction zone appears to be releasing most of its stress right now. But between the shallow brittle zone and the deep ductile zone is a transition region, and that transition region is where things get complicated. Scientists studying the Hikurangi subduction zone have identified a specific depth range, roughly between 10 and 30 kilometers, where the fault appears to be capable of both slow slip events and regular earthquakes. This is the zone where today's 3 earthquakes occurred, 10 kilometers depth, right at the upper edge of that transition region. The question that seismologists are asking right now is whether those 3 earthquakes represent normal brittle failure of small patches of the fault, or whether they're the leading edge of a slow slip event that's just beginning to propagate through the system. GPS data will answer that question over the next several days. If a slow slip event is happening, GPS stations on the North Island will begin detecting motion. The land surface will shift very slightly in a direction consistent with the plate boundary slipping beneath it. The displacement will be measured in millimeters, but it will be detectable. And if the motion continues over days or weeks, seismologists will know they're watching a slow slip event in real time. The alternative is that the 3 earthquakes are isolated events, random failures of small fault patches under normal tectonic stress. In that case, the GPS stations won't detect any anomalous motion, the seismicity will taper off, and the system will return to its background state. But even if this swarm turns out to be nothing, even if it's just noise, the broader context matters, because the Hikurangi subduction zone is not in a steady state. It's in a transition, and understanding what that transition looks like is central to understanding the risk. The southern section of the Hikurangi subduction zone, the part beneath Wellington and the Wairarapa, is locked. GPS measurements show that the land surface is being compressed. The plate boundary is stuck, stress is accumulating, and that stress will eventually be released in an earthquake. The only questions are when and how large. Research published over the past 5 years has given scientists a better understanding of the timeline. Geological evidence from sediment cores drilled along the coast shows that the southern Hikurangi subduction zone has produced at least 10 large earthquakes over the past 7,000 years. The average recurrence interval between those earthquakes is about 500 years. The last event was approximately 571 years ago. That doesn't mean the next earthquake will happen tomorrow. Recurrence intervals are averages. Some earthquake cycles are shorter, some are longer. But it does mean that statistically, the southern section of the fault is in the part of its earthquake cycle where the probability of rupture is elevated. Scientists have calculated that probability. The number they've arrived at is 26%. That's the probability of a magnitude 8.0 or larger earthquake occurring on the southern Hikurangi subduction zone within the next 50 years. 26% might not sound high, but in seismology, a 26% probability over 50 years is a very serious number. For comparison, the probability of a magnitude 7.0 or larger earthquake occurring on the southern San Andreas Fault in California within the next 30 years is about 75%. The Hikurangi number is lower, but it's in the same category of concern. And the consequences of a magnitude 8 earthquake on the Hikurangi subduction zone would be catastrophic in ways that are difficult to overstate. A magnitude 8 subduction earthquake beneath the lower North Island would produce shaking that lasts for minutes, not seconds, minutes, The 2011 Christchurch earthquake in New Zealand, which killed 185 people and caused billions of dollars in damage, produced shaking that lasted about 10 seconds. A magnitude 8 subduction earthquake could produce shaking that lasts 4 to 8 minutes. The duration matters because structures that can survive 10 seconds of shaking can't necessarily survive 8 minutes. Buildings flex. Foundations settle. Unreinforced masonry fails. Even well-designed structures experience cumulative damage that increases with every additional second of shaking. And then there's the tsunami. A magnitude 8 earthquake on the shallow part of the Hikurangi subduction zone would displace the seafloor. The exact amount of displacement depends on the details of the rupture, but for a magnitude 8 event, vertical displacement of several meters is plausible. When the seafloor moves upward by several meters, it lifts the entire water column above it. That water has to go somewhere. It spreads outward as a tsunami. The east coast of the North Island is close to the trench. Very close. In some locations, the shoreline is only 30 to 50 kilometers from the plate boundary. A tsunami generated by a shallow subduction earthquake in that geometry would reach the coast in minutes. Not hours, minutes. Official tsunami warnings take time to issue. Automated systems can detect an earthquake and generate a preliminary warning within seconds, but confirming the magnitude, modeling the tsunami, and disseminating the warning to the public takes minutes. For a local tsunami generated by the Hikurangi subduction zone, there may not be enough time for an official warning to reach coastal communities before the first wave arrives. That's why the public safety messaging in New Zealand emphasizes natural warning signs. If you feel a strong earthquake, or if you feel a weak earthquake that lasts more than a minute and you're near the coast, you don't wait for an official warning. You move immediately to higher ground or as far inland as you can. The earthquake itself is the warning. Scientists have modeled the consequences of a magnitude 9 earthquake on the Hikurangi subduction zone. Magnitude 9 is possible. It's at the upper end of what the fault system is thought to be capable of, but it's not outside the range of historical precedent for subduction zones of this type. The 2004 Sumatra earthquake was magnitude 9.1. The 2011 Tohoku earthquake in Japan was magnitude 9.0. Both of those events occurred on subduction zones with geometries similar to Hikurangi. The modeling results are sobering. A magnitude 9 earthquake on the Hikurangi subduction zone would produce severe to extreme shaking across the entire North Island and the northern South Island. The shaking would last 4 to 8 minutes. Assuming a 70% evacuation success rate for coastal areas, the death toll would exceed 22,000 people. Most of those deaths would be from the tsunami, not the earthquake itself. Another 26,000 people would be injured. Approximately 400,000 people would be displaced from their homes. 30,000 homes would be destroyed or severely damaged by the tsunami alone. The economic cost would exceed 144 billion New Zealand dollars. That's building damage, infrastructure damage, and economic disruption. It doesn't include the cost of long-term recovery, the loss of productivity, or the social and psychological impacts on affected communities. A magnitude 9 earthquake on the Hikurangi subduction zone would be the largest natural disaster in New Zealand's recorded history, by a significant margin. And the fault system capable of producing that event is the same fault system that just produced 3 shallow earthquakes in 24 hours. Now, to be absolutely clear, 3 magnitude 4 to 5 earthquakes do not indicate that a magnitude 9 event is imminent. The overwhelming probability is that today's earthquakes are either isolated events or the beginning of a slow slip event that will release stress gradually over weeks without producing any damaging shaking. But the fact that the swarm is happening at all in this location, at this depth, on this fault, is a reminder that the Hikurangi subduction zone is not dormant, it's active, it's moving, and the motion it's capable of includes scenarios that would reshape the geography and the history of New Zealand. The question now is what the GPS data will show over the next several days, because if this is a slow slip event, the implications extend far beyond today's earthquakes. Slow slip earthquakes were first discovered in 2002, not in New Zealand. The first documented slow slip events were observed in the Cascadia subduction zone in the Pacific Northwest of the United States and in the Nankai Trough subduction zone in Japan. The discovery was accidental. Seismologists had deployed networks of GPS stations to measure the slow, steady motion of tectonic plates. The expectation was that GPS stations would record gradual linear displacement over time as the plates moved past each other at their long-term average rates, a few centimeters per year. Smooth, predictable. What they found instead was periodic, episodic motion. GPS stations would sit still for months or years, recording no displacement at all. Then, over the course of a few weeks, they would suddenly shift by several centimeters in a direction consistent with the plate boundary slipping beneath them. Then the motion would stop. The stations would sit still again. And then, months or years later, the cycle would repeat. This was not normal. Normal earthquakes produce instantaneous displacement. The fault slips in seconds. The GPS station records a sudden jump, but these events were different. The displacement accumulated gradually over weeks. The fault was slipping, but it was slipping slowly, too slowly to produce seismic waves that could be detected by normal earthquake monitoring equipment, too slowly to cause shaking, but fast enough to release energy equivalent to a magnitude 6 or magnitude 7 earthquake. Scientists called them slow slip events, or silent earthquakes, or slow earthquakes. The terminology varied, but the phenomenon was the same. Parts of subduction zones were failing in a fundamentally different way than conventional earthquakes. The discovery raised obvious questions. Why do some parts of a fault slip slowly while other parts slip suddenly? What controls the transition between the two types of behavior? And most importantly, what does slow slip have to do with regular damaging earthquakes? New Zealand became central to answering those questions because the Hikurangi subduction zone produces some of the best documented slow slip events in the world. And it produces them in a location where scientists can study them in extraordinary detail. The first slow slip event detected on the Hikurangi subduction zone was in 2002, the same year slow slip was first discovered elsewhere. GPS stations near Gisborne, on the eastern coast of the North Island, recorded displacement consistent with the plate boundary slipping beneath them over several weeks. The energy released was equivalent to a magnitude 6.5 earthquake, but nobody felt anything. The motion was too slow. Since then, scientists have documented dozens of slow slip events on the Hikurangi subduction zone. Some of them happen offshore, detected only by seafloor instruments and GPS networks. Some of them happen beneath the land, detected by GPS stations on the surface. The events vary in size, duration, and location, but they follow a pattern. The northern section of the subduction zone, offshore from Gisborne and Hawke's Bay, produces slow slip events roughly every 1 to 2 years. The events occur at shallow depths, sometimes as shallow as 2 to 5 kilometers below the sea floor. That's extraordinarily shallow for a subduction zone process. And it makes the Hikurangi subduction zone globally unique. Nowhere else in the world do slow slip events occur at such shallow depths in such a well-instrumented setting. Further south, beneath the Kapiti Coast and Manawatu regions, slow slip events happen roughly every 5 years. These events occur deeper, at depths of 15 to 40 kilometers. They last longer, sometimes several months, and they release more energy. One slow slip event in 2016, triggered by the Kaikoura earthquake, released energy equivalent to a magnitude 7.4 earthquake. The pattern is clear. Slow slip events are not rare anomalies. They're a regular, repeating feature of the Hikurangi subduction zone. They're how the northern section of the fault releases most of its accumulated stress. But understanding that slow slip events exist is different from understanding why they exist. And it's different from understanding what they mean for earthquake hazard. The breakthrough came in 2023 when a team of international researchers published the results of a detailed imaging study of the Hikurangi subduction zone. They used seismic waves from earthquakes around the world to create a 3D picture of the subsurface structure beneath the North Island. What they found was unexpected. The images showed that the subducting Pacific plate was carrying water and water-rich sediments down into the subduction zone. This isn't unusual. All subduction zones carry water down with the subducting plate. But the Hikurangi subduction zone was carrying more water than expected, and that water was being trapped in specific locations. The images showed seamounts, extinct underwater volcanoes on the Pacific plate, being subducted beneath the North Island. As the seamounts descended, they dragged large amounts of water-saturated sediment down with them. That sediment created pockets of high fluid pressure at the plate boundary, and high fluid pressure reduces friction. When friction is reduced, the fault can slip more easily. The researchers found a direct spatial correlation between the locations of subducted seamounts and the locations of slow slip events. Where seamounts had been subducted, slow slip events occurred. Where no seamounts had been subducted, the fault was locked. This was a major discovery. It suggested that slow slip events aren't random. They're controlled by the physical properties of the plate boundary, specifically by the amount of water present and the pressure of that water. And it suggested that the transition between slow slip and regular earthquakes might be controlled by the same factors. But here's where the story gets more complicated. Because while the discovery explained why slow slip events happen, it also raised a new question. If fluid pressure controls whether a fault slips slowly or suddenly, what happens when a slow slip event changes the fluid pressure at a neighboring section of the fault? The answer appears to be that slow slip events can trigger regular earthquakes. In 2016, the Kaikoura earthquake provided a natural experiment. The magnitude 7.8 main shock triggered slow slip events on the Hikurangi subduction zone within hours. But the slow slip events didn't just happen. They propagated. The motion started in one location and spread to neighboring locations over days and weeks. And as the slow slip events propagated, they triggered thousands of small earthquakes along their leading edge. The seismicity wasn't random. It was clustered at the boundary between the region that was slipping slowly and the region that was still locked. The slow slip was loading the locked section with stress, and that stress was being released in earthquakes. The researchers monitoring this process realized they were watching something profound. They were watching slow slip events transfer stress to locked fault segments. They were watching the transition zone between the two types of fault behavior, and they were watching it happen in real time. That observation led to an uncomfortable hypothesis. If slow slip events can trigger small earthquakes at the boundary between slipping and locked regions, can they trigger large earthquakes? The hypothesis is testable. You look at the historical record of large subduction earthquakes worldwide, and you check whether any of them were preceded by slow slip events. The answer is yes, some of them were. Before the 2011 Tohoku earthquake in Japan, the magnitude 9.0 event that killed 18,000 people and triggered the Fukushima nuclear disaster, there was a slow slip event. GPS stations detected anomalous motion in the weeks before the main shock. At the time, nobody knew what it meant. In retrospect, it appears to have been a precursor. Before the 2014 Iquique earthquake in Chile, a magnitude 8.1 event, there was a slow slip event. Seismologists detected unusual seismicity in the months before the main shock. The slow slip event appears to have loaded the fault segment that eventually ruptured. These are not definitive proof that slow slip causes large earthquakes. Correlation is not causation. Most slow slip events are not followed by large earthquakes. The vast majority of slow slip events release stress harmlessly over weeks or months, and then the system returns to normal. But some slow slip events are followed by large earthquakes. And the fact that it happens at all means that slow slip events are not irrelevant to earthquake hazard. They're part of the system. They're part of the process that leads to failure, which brings us back to today's 3 earthquakes off the coast of New Zealand. If those earthquakes are the leading edge of a slow slip event, and if that slow slip event propagates southward toward the locked section of the Hikurangi subduction zone, then the stress state of the fault changes. The locked section gets loaded with additional stress. The probability of rupture increases. That doesn't mean a magnitude 8 earthquake is imminent. It means the system is in motion. It means the fault is doing something right now. And it means the next several days matter. Because the GPS data over the next week will tell us whether this is a slow slip event or just noise. And if it's a slow slip event, the question becomes how large it is, how long it lasts, and where it propagates. The GPS network across New Zealand's North Island is dense. Extraordinarily dense by global standards. There are more than 200 continuous GPS stations operated by GNS Science and the broader GeoNet monitoring network. These stations record the position of the land surface with millimeter precision, 24 hours a day, 7 days a week. The purpose of this network is to detect exactly the kind of motion we're discussing. When a slow slip event occurs on the Hikurangi subduction zone, the plate boundary beneath the North Island slips. The overlying land moves in response. GPS stations detect that motion. The motion is not large. A typical slow slip event might displace the land surface by 2 to 5 centimeters over several weeks. That's roughly the width of your thumb. But GPS stations can detect displacement at the sub-millimeter level, which means they can detect the start of a slow slip event within days of it beginning. The signature of a slow slip event in GPS data is distinctive. Instead of gradual, linear motion consistent with steady plate convergence, the stations show rapid displacement in a specific direction over a period of days to weeks, followed by a return to normal behavior. The direction of displacement points toward the section of the fault that is slipping. If the 3 earthquakes that occurred this morning are the leading edge of a slow slip event, GPS stations near the epicenter, locations should start showing displacement within the next 24 to 72 hours. The displacement will be small at first, maybe a few millimeters, but it will be measurable. The scientists monitoring this system are not waiting passively for the data to accumulate. They're watching in real time. GPS data is processed continuously, with updates available within hours of being recorded. If a slow slip event is beginning, the teams at GNS Science will know about it almost immediately. But here's the challenge. Not all earthquake swarms are associated with slow slip events. Sometimes earthquakes cluster in time and space because of normal stress redistribution following an initial rupture. An earthquake on one part of a fault loads neighboring parts of the fault with stress. Those neighboring parts fail, producing additional earthquakes. The process can cascade for hours or days before the stress field stabilizes and the seismicity tapers off. Distinguishing between a swarm driven by normal stress redistribution and a swarm driven by an underlying slow slip event requires looking at the GPS data. If there's no anomalous GPS motion, it's probably just a normal swarm. If there is anomalous GPS motion, it's probably a slow slip event. The other piece of evidence that seismologists look for is the spatial pattern of the earthquakes. Slow slip events don't produce random seismicity. They produce earthquakes clustered at the leading edge of the slipping region, where the slow slip is loading the locked fault segments. If today's earthquake swarm is associated with a slow slip event, additional earthquakes should occur at the boundary of the slipping region over the next several days. The challenge is that we don't know yet where the boundary is. The 3 earthquakes that occurred this morning are data points, but they're not enough to define the full extent of the slipping region. More data is needed. That data will come from 2 sources. GPS stations will detect the surface motion, and seismometers will detect additional earthquakes. If both data sets show consistent patterns over the next 72 hours, scientists will be able to confirm whether a slow slip event is happening. If a slow slip event is confirmed, the next question is how large it will be. Slow slip events on the Hikurangi subduction zone vary enormously in size. The smallest events release energy equivalent to a magnitude 6.0 earthquake. The largest events release energy equivalent to a magnitude 7.4 earthquake or more. The difference matters because larger events transfer more stress to neighboring fault segments. The duration also matters. Some slow slip events last a few weeks. Others last several months. The longer the event lasts, the more stress gets transferred, and the location matters most of all. If the slow slip event is confined to the northern section of the subduction zone, offshore from Gisborne and Hawke's Bay, it's unlikely to have much impact on the locked southern section beneath Wellington. The 2 sections are separated by a transition zone where the fault behavior changes. Stress doesn't propagate easily across that transition. But if the slow slip event extends into the transition zone, or if it propagates southward toward the locked section, the implications change. The locked section gets loaded. The probability of a large earthquake increases. Scientists studying the Hikurangi subduction zone have been monitoring exactly this kind of scenario for years. They've been watching for slow slip events that might trigger larger earthquakes, and they've been refining their understanding of how stress transfers from the slowly slipping northern section to the locked southern section. The research suggests that the most dangerous scenario is not a slow slip event on the northern section of the fault. The northern section slips slowly all the time. That's normal. The most dangerous scenario is a slow slip event that starts in the north and propagates southward into the transition zone, loading the locked section with stress at a time when that section is already close to failure. That's the scenario scientists are watching for, and that's the scenario that the GPS data over the next several days will either confirm or rule out. It's worth emphasizing again that the overwhelming probability is that today's earthquakes are either isolated events or the beginning of a routine slow slip event that will release stress harmlessly over several weeks. This is not a prediction that a magnitude 8 earthquake is imminent. This is an explanation of the process that scientists are monitoring and the data they're watching. But the fact that the monitoring is happening at all, the fact that there's a network of GPS stations and seismometers and research teams dedicated to understanding this specific fault system, is a testament to how seriously the scientific community takes the hazard. Because the consequences of getting this wrong, of missing the warning signs of a major earthquake, are measured in tens of thousands of lives. There is a historical event that sits in the background of every discussion about the Hikurangi subduction zone. It happened in 1947, and it's the closest thing New Zealand has to a modern example of what a large Hikurangi subduction earthquake actually looks like. On March 25, 1947, at 10:03 a.m. local time, a magnitude 7.0 earthquake struck offshore from Gisborne on the northeastern coast of the North Island. The shaking was strong enough to be felt across much of the region, but the damage on land was relatively minor. A few chimneys collapsed. Some windows broke. Nothing catastrophic. 20 minutes later, at 10:23 a.m., a second earthquake struck. Also magnitude 7.0. Same general location. Same depth. This wasn't an aftershock. This was a second main shock, a twin earthquake on an adjacent segment of the fault. The shaking from the second earthquake was comparable to the first, strong but not devastating. The buildings that had survived the first shock mostly survived the second. The death toll from the earthquakes themselves was minimal, but then the tsunami arrived. The twin earthquakes had occurred on the shallow part of the Hikurangi subduction zone, close to the trench. The fault rupture displaced the sea floor. Water was pushed upward and outward. The tsunami propagated toward the coast at hundreds of kilometers per hour. The first wave arrived approximately 30 to 40 minutes after the earthquakes. In some locations along the coast, the wave height exceeded 10 meters. That's 33 feet. A 3-story building worth of water moving inland at speed. Coastal communities had no warning. There was no tsunami alert system in 1947. The concept of a tsunami warning network didn't exist yet. The Pacific Tsunami Warning Center, which monitors earthquakes across the Pacific Ocean and issues tsunami alerts, wasn't established until 1949, 2 years after the Gisborne earthquakes. People in coastal areas felt the earthquakes. They felt the shaking. But many of them didn't know that shaking near the coast means you move to higher ground immediately. Some people went back to their homes after the shaking stopped. Some people went down to the beach to see what had happened. And when the tsunami arrived, it caught them completely unprepared. The death toll was never precisely documented, partly because some victims were swept out to sea and never recovered. The official estimate is at least 10 people killed, but local accounts suggest the number may have been higher. The economic damage was severe. Coastal buildings were destroyed. Fishing boats were smashed. Agricultural land was inundated with salt water. The recovery took months. In some areas, the landscape was permanently altered. Sandbars shifted. River mouths changed course. The tsunami reshaped the coast. The 1947 Gisborne earthquakes are important for 2 reasons. First, they demonstrate that the northern Hikurangi subduction zone is capable of producing tsunami-genic earthquakes. The fault can rupture the shallow section close to the trench, and when it does, it generates tsunamis large enough to kill people and destroy coastal infrastructure. Second, The twin earthquake sequence demonstrates that the northern section of the fault can fail in complex ways. Two magnitude 7.0 earthquakes 20 minutes apart on adjacent fault segments is not a simple rupture. It's a cascading failure. The first earthquake loaded the neighboring fault segment with stress. That segment failed 20 minutes later. That cascading failure pattern is consistent with what scientists have learned about slow slip events and stress transfer. When one part of a fault slips, it loads neighboring parts. Sometimes those neighboring parts fail immediately, producing aftershocks or twin earthquakes. Sometimes they fail slowly, producing slow slip events. And sometimes they stay locked, accumulating stress until a later failure. The 1947 earthquakes occurred on the northern section of the Hikurangi subduction zone, the same section where today's earthquake swarm is occurring. That doesn't mean today's swarm will produce a repeat of 1947. The circumstances are different. The magnitude of today's earthquakes is lower. The depth is similar, but the geographic location is slightly different. But the 1947 precedent is a reminder that the northern section of the fault is not benign. It's capable of producing damaging earthquakes and deadly tsunamis. And it's capable of failing in ways that are difficult to predict. There's another historical event that matters to this discussion, even though it occurred much further back in time. In 1931, a magnitude 7.8 earthquake struck Hawke's Bay, further south along the North Island's eastern coast. The epicenter was on land, not offshore, but the earthquake is believed to have occurred on one of the large thrust faults associated with the Hikurangi subduction zone. The 1931 Hawke's Bay earthquake remains New Zealand's deadliest natural disaster in recorded history. 256 people were killed. The cities of Napier and Hastings were devastated. Buildings collapsed. Fires broke out. The shaking lasted approximately 2.5 minutes, long enough to cause catastrophic damage to unreinforced masonry structures. The earthquake also caused permanent uplift of the land. Parts of the Hawke's Bay coastline rose by more than a meter. The harbor at Napier, which had been navigable, became too shallow. The tsunami that followed the earthquake was relatively small, but the combination of shaking, fire, and structural collapse made the 1931 event a defining moment in New Zealand's history. The 1931 earthquake is relevant because it demonstrates what a magnitude 7.8 event on the Hikurangi system can do on land. And magnitude 7.8 is at the lower end of what the locked southern section of the subduction zone is capable of producing. A magnitude 8.0 or larger event would be significantly more powerful. The energy released by an earthquake scales exponentially with magnitude. A magnitude 8.0 earthquake releases approximately 5.6 times more energy than a magnitude 7.8 earthquake. A magnitude 9.0 earthquake releases approximately 32 times more energy than a magnitude 8.0 earthquake. The difference between a magnitude 7.8 event, like the 1931 Hawke's Bay earthquake, and a magnitude 9.0 event, like the 2011 Tohoku earthquake in Japan, is a factor of nearly 180 in total energy release. The point is not to predict that a magnitude 9.0 earthquake is coming. The point is to understand the scale of what the Hikurangi subduction zone is capable of producing, and to place today's earthquake swarm in that context. 3 magnitude 4 to 5 earthquakes do not indicate that a magnitude 9.0 event is imminent, but they do indicate that the fault is active. They indicate that stress is being redistributed, and they indicate that the system is doing something right now in real time that seismologists are watching closely, because the historical record tells us that this fault system doesn't stay quiet forever. It ruptures. It has ruptured before. And it will rupture again. The only questions are when, where, and how large. While the northern section of the Hikurangi subduction zone releases stress through slow slip events, the southern section is doing something very different. It's locked. And that locked section is what keeps seismologists awake at night. GPS data shows that the land surface across the lower North Island, from roughly the Manawatu region down to Wellington and the Wairarapa, is being compressed. The plate convergence is happening, but the plate boundary beneath this region is not slipping. The stress is accumulating. When a fault is locked, the rock on both sides of the fault is stuck together by friction. The tectonic plates are pushing against each other, but the fault isn't moving. The rock deforms elastically, like a spring being compressed. Strain builds up in the rock surrounding the fault. That strain represents stored energy. Eventually, the stress exceeds the strength of the rock. The fault fails. The stored energy is released suddenly in an earthquake. The rock on both sides of the fault rebounds to its undeformed state, and the cycle starts again. This is the classic earthquake cycle, and it's what's happening on the southern Hikurangi subduction zone right now. The fault is locked, the strain is building, and the next earthquake is coming. The question is when. Geological evidence suggests that the southern section of the Hikurangi subduction zone ruptures approximately every 500 years on average. The last major earthquake on this section occurred approximately 571 years ago, in 1455 AD, give or take 25 years. If the average recurrence interval is 500 years, and the last event was 571 years ago, then statistically speaking, the fault is overdue. But overdue is a complicated term in seismology. Recurrence intervals are averages. Some cycles are shorter, some are longer. The variation can be 100 years or more in either direction. So the fact that 571 years have passed since the last event doesn't mean the next event will happen tomorrow. It means the fault is in the part of its cycle where the probability of rupture is elevated. It means the stress has been building for more than 500 years. And it means that every additional year that passes without an earthquake is another year of accumulated strain. Scientists have calculated the probability of a major earthquake on the southern Hikurangi subduction zone. The number is 26% over the next 50 years. That's the probability of a magnitude 8.0 or larger event. 26% is not a high probability in absolute terms. It's not 50-50. It's not even 1 in 3. But in the context of earthquake hazard, 26% is high enough to drive major policy decisions. For comparison, the probability of a magnitude 7.0 or larger earthquake on the southern San Andreas Fault in California over the next 30 years is approximately 75%. That's considered a very high probability, and it drives building codes, insurance requirements, and public preparedness campaigns across Southern California. The 26% probability for the Hikurangi subduction zone is lower than the California number, but it's in the same category of concern. It's high enough that the New Zealand government has invested heavily in earthquake and tsunami preparedness. It's high enough that building codes have been updated. It's high enough that public education campaigns emphasize the natural warning signs of a tsunami. And it's high enough that every earthquake swarm on the Hikurangi subduction zone, including today's 3 events, gets immediate attention from the scientific community. Because if today's swarm is associated with a slow slip event, and if that slow slip event propagates southward from the northern section into the transition zone, the stress state of the locked southern section changes. Additional stress gets loaded onto a fault segment that's already close to failure. That doesn't guarantee an earthquake. Most slow slip events don't trigger large earthquakes, but it changes the probability. It moves the system incrementally closer to the threshold. The transition zone between the northern and southern sections of the Hikurangi subduction zone is not well defined. It's not a sharp boundary. It's a gradual transition over several tens of kilometers, where the fault behavior changes from creeping and slow slip to locked and accumulating stress. GPS data and seismicity patterns suggest that the transition zone is located roughly between Hawke's Bay and the Manawatu region. The northern boundary of the locked section is somewhere in that area. But the exact location is uncertain, and it may vary over time as the fault system evolves. What scientists know from modeling and from observations of other subduction zones around the world is that transition zones are often the locations where large earthquakes initiate. The transition between locked and creeping sections creates stress concentrations. And stress concentrations are where faults fail. If a slow slip event loads the transition zone with additional stress, and if that stress concentration reaches the failure threshold, the result could be an earthquake that ruptures both the transition zone and the locked southern section in a single event. That's the scenario that produces magnitude 8.0 or larger earthquakes. The 2011 Tohoku earthquake in Japan appears to have initiated in exactly this way. The main shock began in a transition zone between a shallow locked section and a deeper creeping section. The rupture propagated upward and outward, eventually breaking the entire locked section and producing a magnitude 9.0 earthquake. The analogy is not perfect. The Hikurangi subduction zone is not identical to the Japanese subduction zone. The geometry is different. The convergence rate is different. The sediment structure is different, but the basic physics is the same. Transition zones are dangerous. They're where large earthquakes start. And if today's earthquake swarm is associated with a slow slip event that propagates into the transition zone, the southern Hikurangi subduction zone is one step closer to the next major earthquake. The GPS data over the next several days will be critical. If the GPS stations in the Manawatu and Hawke's Bay regions start showing anomalous motion, it means the slow slip event is propagating southward. It means the transition zone is being loaded, and it means the probability calculation changes. Scientists will be watching the data closely, not because they expect a magnitude 8 earthquake to occur immediately, but because slow slip events are one of the few observable precursors to large subduction earthquakes. They're measurable, they're trackable, and in some cases, they provide days or weeks of warning before a main shock. That warning is not a prediction, it's not a guarantee that an earthquake will occur, but it's information. And in earthquake hazard, information is the difference between preparedness and surprise. In 2023, a team of researchers published one of the most important papers on the Hikurangi subduction zone in recent memory. The paper didn't make international headlines. It was published in a peer-reviewed scientific journal, discussed among specialists, and then filed away in the growing body of knowledge about subduction zone mechanics. But what the paper revealed was profound. It showed that the strange behavior of the Hikurangi subduction zone, the slow slip events, the shallow seismicity, the complex patterns of locking and creep, all of it could be explained by a single geological feature: subducted seamounts. Seamounts are underwater volcanoes. Most of them are extinct, formed millions of years ago when tectonic conditions were different. They rise from the ocean floor as isolated peaks, sometimes reaching heights of several thousand meters. On the Pacific Plate, there are hundreds of seamounts scattered across the sea floor. As the Pacific Plate subducts beneath New Zealand, those seamounts are carried down with it. They don't disappear. They don't melt immediately. They descend into the subduction zone, maintaining their structure and their buoyancy for tens of kilometers as they're forced deeper into the Earth. The research team used seismic imaging to create a 3D picture of the subsurface beneath the North Island. They were looking for the seamounts, and they found them. The images showed seamounts at various stages of subduction. Some were just entering the trench. Some were at depths of 5 to 10 kilometers. Some were deeper still, approaching 20 kilometers. And the pattern was clear. Every location where seamounts had been subducted corresponded to a location where slow slip events occurred. The correlation was not subtle, it was direct. Where seamounts went down, slow slip happened. Where no seamounts went down, the fault was locked. The mechanism appears to be fluid pressure. Seamounts are porous. They contain water in their fractures and in the sediments surrounding them. As the seamounts are subducted and compressed, that water is squeezed out. It migrates along the plate boundary. And high-pressure water reduces friction. When friction is reduced, the fault can slip more easily. Instead of accumulating stress until it fails suddenly in a large earthquake, the fault slips gradually in a slow slip event. The seamount essentially lubricates the fault. But seamounts don't subduct uniformly. They're discrete features. A seamount at the plate boundary creates a localized zone of reduced friction, but the fault segments on either side of the seamount where no water is being released remain locked. This creates a patchwork of locked and slipping regions along the fault. And that patchwork is what drives the complex behavior of the Hikurangi subduction zone. The discovery has major implications for understanding earthquake hazard. It suggests that the locations of slow slip events are not random. They're controlled by the geometry of the subducting plate. They're controlled by where seamounts happen to be. And it suggests that the locked sections of the fault, the sections where no seamounts are being subducted, are the sections most likely to rupture in large earthquakes. The southern Hikurangi subduction zone, the locked section beneath Wellington and the Wairarapa, doesn't have subducting seamounts in the right locations to promote slow slip. That's why it's locked. That's why stress is accumulating. And that's why the next major earthquake will probably originate there. But here's where the seamount connection becomes directly relevant to today's earthquake swarm. The researchers found something else in the seismic images. They found the ghostly outline of a very large seamount that had been subducted long ago. This seamount was much larger than the ones currently entering the subduction zone, and it had descended to a depth of approximately 40 to 50 kilometers beneath the North Island. The seamount was no longer intact. At those depths, the temperatures and pressures are high enough that the rock begins to partially melt. The seamount was being consumed by the subduction process, but as it broke apart, it released enormous amounts of water. That water was migrating upward along the plate boundary, following the path of least resistance, and the researchers calculated that the water released by this deep seamount could be affecting the shallow parts of the subduction zone tens of kilometers away. In other words, a seamount that subducted decades or centuries ago, now sitting at depths where it's being destroyed, could be influencing the behavior of the fault near the surface today. The 3 earthquakes that occurred this morning at 10 kilometers depth are in exactly the depth range where water released from deep sea mounts might be migrating along the plate boundary. This doesn't prove that today's swarm is related to seamount-derived fluids, but it's consistent with the model, and it raises an important question. If water from deep seamounts is migrating along the plate boundary, and if that water is reducing friction and promoting slow slip, what happens when the water reaches a section of the fault that's already stressed? The answer, according to the researchers, is that the fault fails, either slowly in a slow slip event or suddenly in an earthquake. The seamount connection is one of the reasons scientists are paying close attention to the northern Hikurangi subduction zone. It's not just that slow slip events happen there. It's that the physical conditions that promote slow slip, the high fluid pressures and reduced friction, can also change rapidly if the fluid migration patterns shift. A seamount that's been slowly releasing water for years could suddenly release a large pulse of water if its internal structure fails. That pulse of water could propagate along the plate boundary in days or weeks. And when it arrives at a stressed fault segment, it could trigger a failure. This is speculative. It's at the edge of what the current research can support, but it's the kind of physical process that explains why earthquake swarms like today's matter. Because swarms are not just isolated events, they're symptoms of a system in motion. And understanding what's moving and where it's moving is critical to understanding the hazard. Let's walk through the scenario that seismologists are monitoring right now, not because it's likely, but because it's possible. And because the consequences are large enough that even a small probability demands attention. The scenario begins with today's earthquake swarm being confirmed as the start of a slow slip event. GPS stations near the epicenter locations detect anomalous motion over the next 72 hours. The displacement is consistent with the plate boundary slipping beneath the North Island. Seismometers detect additional earthquakes clustered at the leading edge of the slipping region. Scientists confirm that a slow slip event is underway. The event is centered offshore from Gisborne and the East Cape in the northern section of the Hikurangi subduction zone. This is normal. Slow slip events happen in this location regularly, but this event doesn't stop. Over the course of the next week, the slipping region expands. GPS stations further south in the Hawke's Bay region begin detecting motion. The slow slip is propagating southward. This is less common, but it's not unprecedented. Slow slip events sometimes migrate along the fault. The migration is driven by stress transfer. When one section of the fault slips, it loads the neighboring section with stress. That neighboring section begins to slip. The process cascades. By the end of the second week, the slow slip event has reached the transition zone between the northern creeping section and the southern locked section. GPS stations in the Manawatu region are showing displacement. The slow slip is now loading the northern boundary of the locked section with stress. At this point, two things can happen. In the first scenario, the slow slip event stalls. The locked section doesn't respond. The stress added by the slow slip is not enough to overcome the friction holding the locked section in place. The slow slip event gradually tapers off over the next several weeks. The system returns to normal. Nothing catastrophic occurs. This is the most likely outcome. Most slow slip events do not trigger large earthquakes. The stress transfer is real, but it's usually not large enough to bring a locked fault segment to failure. In the second scenario, the locked section responds. The additional stress from the slow slip event is enough to tip the balance. The northern edge of the locked section begins to slip, and once it starts slipping, it doesn't stop. The rupture propagates southward through the locked section. It accelerates. The slip velocity increases from centimeters per day to meters per second. The slow slip transition into a regular earthquake, a large earthquake. The exact magnitude depends on how much of the locked section ruptures. If only the northern edge fails, the earthquake might be magnitude 7.5 to 8.0. If the entire locked section ruptures, the earthquake could be magnitude 8.5 or larger. If the rupture breaks through to the shallow part of the subduction zone near the trench and displaces the sea floor significantly, the earthquake could approach magnitude 9.0. The shaking would be felt across the entire North Island and the northern South Island. The duration would depend on the rupture length, but for a large subduction earthquake, shaking durations of 4 to 8 minutes are typical. The tsunami would begin generating immediately. The seafloor displacement would occur over the course of the rupture, which might last 2 to 3 minutes for a magnitude 8.5 event. The water column above the rupture would be displaced upward. Tsunami waves would radiate outward in all directions. The first waves would reach the east coast of the North Island within minutes. The exact arrival time depends on the location along the coast and the depth of the rupture, but for a shallow rupture close to the trench, arrival times of 10 to 20 minutes are typical. That's not enough time for official warnings. Automated tsunami warning systems can detect the earthquake and generate a preliminary alert within seconds, but confirming the tsunami and disseminating the warning to the public takes minutes. For the communities closest to the epicenter, the earthquake itself would be the only warning. The modeling results that scientists have published show that a magnitude 9.0 earthquake on the southern Hikurangi subduction zone, assuming 70% evacuation success, would kill more than 22,000 people. Most of those deaths would be from the tsunami. The earthquake shaking would cause building collapses and injuries, but the tsunami is the primary killer in subduction zone disasters. Another 26,000 people would be injured. Approximately 400,000 people would be displaced from their homes. The economic cost would exceed 144 billion New Zealand dollars. Those numbers are scenario-based. They're not predictions. They're estimates of what would happen if a specific earthquake occurred. But they're based on realistic assumptions about building vulnerability, tsunami inundation modeling, and evacuation behavior. The scenario I've just described, the slow slip event that propagates south and triggers a magnitude 8 or larger earthquake, is not the expected outcome of today's earthquake swarm. The expected outcome is that the swarm is either isolated seismicity or a routine slow slip event that releases stress harmlessly. But the scenario is physically plausible. It's consistent with what scientists know about how subduction zones fail. And it's exactly the scenario that the GPS monitoring network is designed to detect. If the scenario begins to unfold, if the GPS data over the next several days shows that a slow slip event is propagating southward toward the locked section, scientists will see it. They'll track it in real time. They'll communicate the observations to civil defense authorities, and those authorities will make decisions about whether to elevate public warnings. New Zealand does not have a formal earthquake early warning system like Japan or California. The technology exists, but the implementation is still in the planning stages. What New Zealand does have is a sophisticated understanding of the natural warning signs of earthquakes and tsunamis, and a public education campaign designed to ensure that people know how to respond. The messaging is simple. If you feel a strong earthquake, or if you feel a weak earthquake that lasts more than a minute and you're near the coast, you move immediately to higher ground or as far inland as you can. You don't wait for an official warning. You don't check your phone. You don't gather your belongings. You move. That messaging has been drilled into the population through schools, community organizations, and media campaigns. The hope is that if a large Hikurangi earthquake occurs, enough people will respond correctly to reduce the death toll significantly below the modeled worst case. But hope is not a plan. In the scenario I've described, the slow slip event that triggers a magnitude 8 or larger earthquake is one of the scenarios that keeps emergency managers awake at night, because it's the scenario where the warning time is measured in minutes, not hours, and minutes are not enough to evacuate 400,000 people. On November 14, 2016, at just after midnight local time, a magnitude 7.8 earthquake struck the northeastern South Island of New Zealand. The epicenter was near the town of Kaikoura, a small coastal community known for its whale watching and marine wildlife. The Kaikoura earthquake was one of the most complex earthquakes ever recorded. It ruptured at least 12 different faults simultaneously. Some of those faults were known. Some had never been mapped. The rupture propagated northward for more than 170 kilometers, breaking fault after fault in a cascading failure that lasted more than 2 minutes. The shaking was severe across a wide area. The town of Kaikoura was cut off for days. The main highway and the railway line were destroyed by landslides. Parts of the coast were uplifted by several meters. The sea floor rose. Seal colonies that had been underwater were suddenly above the high tide line. 2 people were killed. Given the magnitude and duration of the shaking, that's an extraordinarily low death toll. It's a testament to New Zealand's building codes and the fact that the earthquake occurred in a relatively sparsely populated area. But the Kaikoura earthquake matters to the current story not because of what it did on the South Island, but because of what it triggered on the North Island. Within hours of the main shock, GPS stations across the lower North Island began detecting motion. The motion wasn't random, it was systematic, consistent with the plate boundary beneath the North Island slipping. A slow slip event had been triggered, not one slow slip event. Multiple slow slip events in different locations, all triggered by the stress changes from the Kaikoura earthquake hundreds of kilometers away. The largest of these triggered slow slip events occurred beneath the Kapiti Coast and Manawatu regions. The event released energy equivalent to a magnitude 7.4 earthquake. Over the course of several months, the plate boundary slipped by tens of centimeters. GPS stations tracked the motion in real time. The Kaikoura earthquake also triggered slow slip beneath Hawke's Bay and in other locations along the Hikurangi subduction zone. The stress transfer from the South Island rupture had reached across the complex fault geometry of the lower North Island and set off a chain reaction. Scientists studying the Kaikoura earthquake and its aftermath realized they were watching something profound. They were watching a demonstration of how interconnected fault systems are. They were watching stress propagate across regions that are separated by hundreds of kilometers, and they were watching slow slip events respond to stress changes on timescales of hours to days. The Kaikoura earthquake provided natural experiments that would have been impossible to design. It showed that slow slip events can be triggered by distant earthquakes. It showed that slow slip events can cascade, with one event triggering others. And it showed that the Hikurangi subduction zone is exquisitely sensitive to stress changes. That sensitivity is a double-edged sword. On one hand, it means that slow slip events are common, and common slow slip events might be releasing stress harmlessly that would otherwise accumulate toward a large earthquake. On the other hand, it means that the system is operating close to its failure threshold. Small stress perturbations can trigger large responses. The Kaikoura earthquake occurred on faults that are part of the Marlborough Fault System, a complex network of strike, slip, and thrust faults that connect the Hikurangi subduction zone to the Alpine Fault. The Alpine Fault is New Zealand's other major seismic hazard, a strike-slip fault running along the western side of the South Island. The connection between the Kaikoura earthquake and the triggered slow-slip events on the Hikurangi subduction zone demonstrates that these fault systems don't operate independently. They're coupled. Stress changes on one fault can influence another fault hundreds of kilometers away. That coupling raises a question that scientists are still working to answer. If a large earthquake on the Hikurangi subduction zone occurs, will it trigger earthquakes on other faults? Could a magnitude 8 or larger Hikurangi earthquake set off a cascade of failures across the entire fault network of New Zealand? The answer is probably yes. The Kaikoura earthquake demonstrated that cascading failures are possible. Whether they happen in any specific earthquake depends on the details of the rupture, the stress state of the surrounding faults, and factors that are difficult to measure in advance. But the possibility exists. And it's one of the reasons the Hikurangi subduction zone is treated with such serious concern. It's not just that a large Hikurangi earthquake would be devastating in its own right. It's that it could trigger a multi-fault disaster that affects the entire country. The Kaikoura earthquake is also relevant to today's earthquake swarm because it demonstrated how quickly the Hikurangi subduction zone can respond to stress changes. The triggered slow-slip events began within hours of the main shock. The GPS data showed motion almost immediately. If today's earthquake swarm is associated with a slow-slip event, the GPS data will show it within the next 24 to 72 hours. The system doesn't wait. It responds on time scales that are fast by geological standards, even if they're slow by human standards. And that responsiveness is what makes the monitoring possible. Scientists can track what's happening in near real time. They can see the fault moving. They can watch the stress transfer. They can detect the beginning of a cascade before it becomes catastrophic. The challenge is that detecting a slow-slip event is not the same as predicting a large earthquake. Most slow-slip events don't lead to large earthquakes. The signal-to-noise ratio is low. The false alarm rate would be high. But the detection capability exists. And if today's swarm is the beginning of something larger, the monitoring network will see it developing. That's not a guarantee of a successful warning, but it's more information than most earthquake-prone regions in the world have access to. While the northern section of the Hikurangi subduction zone slips slowly, releasing stress in measurable increments, the southern section is doing something very different. It's silent, it's locked, and it's accumulating strain at a rate that seismologists can measure but not predict. GPS stations across the lower North Island show a consistent pattern. The land surface is moving, but it's not moving in the direction you'd expect if the plate boundary were slipping normally. It's moving in the opposite direction. When a subduction zone is slipping freely, the overlying plate moves toward the trench. The land surface gets pulled toward the ocean. GPS stations detect displacement in that direction. That's normal subduction behavior. But when a subduction zone is locked, the overlying plate gets compressed. The land surface moves away from the trench. GPS stations detect displacement in the opposite direction. The pattern is called strain accumulation, and it's the signature of a fault that's stuck. The GPS data across the lower North Island shows strain accumulation. The land is being compressed. The plate boundary is locked. And every year that passes without an earthquake is another year of accumulated elastic strain. The rate of strain accumulation depends on the plate convergence rate. In the southern Hikurangi subduction zone, the convergence rate is approximately 2 to 3 centimeters per year. That's slower than the northern section, but it's still significant over decades and centuries. If the fault has been locked for 571 years, and if the convergence rate is 2 to 3 centimeters per year, then the total accumulated displacement is roughly 11 to 17 meters. That's the amount of slip deficit that has built up since the last major earthquake. When the fault finally ruptures, it won't slip by 11 to 17 meters all at once. Some of that accumulated deficit will be released in the earthquake. Some of it will remain as residual strain. But even a partial release of that accumulated slip could produce a very large earthquake. For comparison, the 2011 Tohoku earthquake in Japan involved slip of up to 50 meters on some parts of the fault. That's what produced a magnitude 9.0 event. The Hikurangi subduction zone probably doesn't have 50 meters of accumulated slip, but it might have enough for a magnitude 8.0 or 8.5 event, and that's large enough to be catastrophic. The challenge with locked faults is that strain accumulation doesn't give you a timeline. It tells you that stress is building. It doesn't tell you when the fault will fail. Some locked faults accumulate strain for centuries before rupturing. Some rupture earlier. The variation depends on factors that are difficult to measure. The exact distribution of stress along the fault, the frictional properties of the fault surface, the presence or absence of fluids that might reduce friction, and countless other variables that influence whether a fault is close to failure or still far from it. What seismologists can say with confidence is that the southern Hikurangi subduction zone is in the late stages of its earthquake cycle. The strain has been accumulating for more than 500 years. The probability of rupture is elevated, and every additional year that passes moves the system incrementally closer to failure. But closer to failure doesn't mean imminent failure. It means the probability is higher than it was 100 years ago. It means the fault is in a state where a stress perturbation, like the kind that might be caused by a slow slip event, could potentially trigger a rupture. The GPS data that seismologists are watching over the next several days will tell them whether today's earthquake swarm is associated with a stress perturbation. If a slow slip event is confirmed, and if that event propagates toward the locked southern section, the stress state changes. The probability calculation updates. That update won't give a prediction. It won't tell you that an earthquake will occur on a specific date, but it will tell you that the system is in motion. It will tell you that the fault is responding to a stress change. And in earthquake science, that kind of information is rare and valuable. Most earthquakes occur without any detectable precursors. The fault goes from locked to ruptured in seconds with no warning. Slow slip events are one of the few phenomena that provide a window into the stress state of a fault in the days or weeks before a possible rupture. That window doesn't guarantee a rupture will occur, but it provides information, and information allows for preparedness. In New Zealand, that preparedness takes specific forms. Building codes are designed to withstand shaking from large subduction earthquakes. Tsunami evacuation zones are mapped for every coastal community. Public education campaigns teach people the natural warning signs of tsunamis. Emergency management agencies have response plans for mass casualty events. None of that prevents an earthquake from occurring, but it reduces the consequences when one does. The 26% probability of a magnitude 8.0 or larger earthquake on the southern Hikurangi subduction zone over the next 50 years is high enough to drive those preparations. It's high enough that the government treats the hazard as a national level risk. And it's high enough that every earthquake swarm, every slow slip event, Every anomaly in the GPS data gets immediate scientific attention because the consequences of being unprepared are measured in tens of thousands of lives. The GPS network across New Zealand's North Island is dense and sophisticated, but GPS stations can only measure what happens at the land surface. They can't tell you what's happening 10 kilometers below the seafloor, where the actual plate boundary is. To monitor the plate boundary directly, scientists have deployed a different kind of instrument. Ocean bottom seismometers and ocean bottom pressure sensors sit on the seafloor, directly above the subduction zone, recording seismic waves and detecting tiny changes in water pressure that indicate seafloor motion. These instruments are expensive, they're difficult to deploy and retrieve, and they operate in a harsh environment where corrosion, current, and marine life create constant challenges. But they provide data that land-based instruments can't. In 2014, scientists deployed the first ocean bottom observatories on the Hikurangi subduction zone as part of a project to monitor slow slip events in real time. The instruments were placed directly above the shallow part of the subduction zone, offshore from Gisborne, where slow slip events occur at depths as shallow as 2 to 5 kilometers below the seafloor. The observatories recorded data continuously for more than a year. What they detected was extraordinary. The instruments captured a slow slip event as it was happening, not from GPS data at the surface, but from direct measurements of seafloor motion and seismicity at the plate boundary itself. The data showed that slow slip events are not smooth, continuous processes. They're episodic, jerky, and full of small earthquakes. The fault doesn't slip steadily. It slips in bursts. Each burst lasts seconds to minutes. Between bursts, the fault locks again, then another burst, then another lock. Over days and weeks, the cumulative slip adds up to tens of centimeters. The small earthquakes occurring during the slip bursts are called tremor. They're different from normal earthquakes. Tremor doesn't produce sharp, impulsive seismic waves. It produces sustained, low-frequency vibrations that can last for minutes or hours. Tremor is the signature of slow slip. When seismologists detect tremor on a subduction zone, they know a slow slip event is happening. The ocean bottom observatories on the Hikurangi subduction zone detected tremor continuously during the slow slip event they recorded. But they also detected something else. They detected ordinary earthquakes, small ones, occurring at the edge of the slipping region. These weren't tremor. These were brittle failures of the rock, the same process that produces damaging earthquakes, just on a much smaller scale. The earthquakes were clustered at the boundary between the region that was slipping slowly and the region that was still locked. The slow slip was loading the locked region with stress, and that stress was being released in small earthquakes. This is exactly the process that seismologists worry about. If the small earthquakes at the edge of a slow slip event can cascade into larger earthquakes, and if those larger earthquakes can trigger a full rupture of the locked section, then slow slip events become a potential precursor to large damaging earthquakes. The ocean bottom data doesn't prove that slow slip events trigger large earthquakes, but it shows that the mechanism is plausible. It shows that slow slip events do transfer stress, and it shows that the stressed regions respond by failing, even if most of the time those failures are small and harmless. The ocean bottom observatories have since been retrieved and redeployed multiple times. The data collection is ongoing, and every slow slip event that gets recorded adds to the growing understanding of how these events work. The relevance to today's earthquake swarm is direct. If the swarm is associated with a slow slip event, the seismicity pattern should resemble what the ocean bottom observatories recorded. Small earthquakes clustered at the leading edge of the slipping region. Tremor if the instruments are sensitive enough to detect it. And possibly larger earthquakes if the stress transfer is significant enough. The seismic network on land is already detecting the earthquakes. 3 magnitude 4 to 5 events in 24 hours. If more earthquakes occur over the next several days, and if those earthquakes cluster in a pattern consistent with slow slip, scientists will know that's what they're looking at. And if the pattern develops further, if the seismicity migrates, or if GPS stations detect motion, the monitoring shifts from routine observation to active tracking of a developing event. That's where the system is right now. Routine observation, watching, waiting for the data to resolve itself into a pattern that makes sense. There's another kind of seismic signal associated with slow slip events, and it occurs at depths where the physics of fault behavior changes in ways that seismologists are still working to understand. It's called deep tremor, and it's one of the strangest seismic phenomena ever documented. Deep tremor was first discovered in Japan in the early 2000s. Seismologists noticed sustained, low-frequency vibrations occurring at depths of 30 to 40 kilometers beneath the surface in the transition zone between the shallow brittle part of the subduction zone and the deeper ductile part. The vibrations didn't look like ordinary earthquakes. They didn't have the sharp onset, the clear P waves and S waves, the impulsive character of brittle failure. They looked more like noise, like a sustained hum in the seismic record. But the noise was correlated with slow slip events. When slow slip occurred, tremor appeared. When slow slip stopped, tremor disappeared. The correlation was too strong to be coincidental. Researchers eventually figured out that deep tremor is made up of thousands of tiny earthquakes occurring in rapid succession. Each individual earthquake is too small to be detected on its own. But when thousands of them occur within seconds, the cumulative signal shows up as a sustained vibration. Deep tremor occurs at the transition between locked and creeping sections of the fault. It occurs where the fault is neither fully stuck nor fully slipping freely. It's the signature of a fault in the process of transitioning from one behavior to the other. On the Hikurangi subduction zone, deep tremor has been detected beneath the Kapiti Coast and Manawatu regions at depths of 30 to 40 kilometers. The tremor occurs episodically, always in association with slow slip events, and it appears to mark the down-dip edge of the slipping region, the boundary where the slow slip transitions into steady creep at greater depths. The importance of deep tremor is that it provides a direct seismic signature of slow slip. GPS data tells you that the surface is moving. Tremor tells you that the fault is slipping. Together, they give a complete picture of what's happening. But deep tremor also raises questions. If tremor occurs at the boundary between slipping and locked regions, and if that boundary is where stress is concentrated, then tremor is marking the exact location where the next earthquake is most likely to initiate. That doesn't mean tremor predicts earthquakes. Most tremor episodes are not followed by earthquakes. But it does mean that tremor is a signal worth monitoring. It tells you where the fault is under stress. It tells you where the system is in motion. And in some cases, it might provide days or weeks of warning before a larger event. On the Hikurangi subduction zone, deep tremor is part of the normal background seismicity. It happens regularly. Seismologists have catalogs of tremor episodes going back years. They know the typical depths, the typical durations, the typical magnitudes. But sometimes tremor behavior changes. Sometimes it becomes more frequent or more intense. Sometimes it migrates along the fault in ways that are unusual. And when that happens, It's a signal that something different is occurring. Today's earthquake swarm is associated with a slow slip event, and if that slow slip event extends to depths where tremor occurs, seismologists will see it in the data. The tremor will appear, it will mark the down dip edge of the slipping region, and it will provide independent confirmation that slow slip is happening. The combination of GPS data showing surface motion, seismicity showing brittle failure at shallow depths, and tremor showing fault slip at greater depths would paint a complete picture of a slow slip event in progress. That picture is what scientists are waiting to see. The data exists, the instruments are recording, the analysis is ongoing, and over the next several days, the pattern will either emerge or it won't. If it emerges, scientists will know they're watching a slow slip event in real time. If it doesn't, today's earthquakes were probably just isolated events, and the system returns to its background state. Either way, the monitoring continues, because the Hikurangi subduction zone doesn't stop moving. It doesn't stop accumulating stress, and the next earthquake, whenever it occurs, will happen on this fault. Part 13. What we don't know. For all the progress that's been made in understanding the Hikurangi subduction zone, there are fundamental questions that remain unanswered. And those unanswered questions are what make events like today's earthquake swarm difficult to interpret in real time. The first question is whether slow slip events make large earthquakes more likely or less likely. On one hand, slow slip events release stress. If the stress is being released gradually through slow slip, it's not accumulating toward a large earthquake. In that sense, slow slip events might reduce earthquake hazard. On the other hand, slow slip events transfer stress. They load neighboring fault segments, and if one of those neighboring segments is already close to failure, the additional stress from a slow slip event might be enough to trigger a rupture. In that sense, slow slip events might increase earthquake hazard. The data supports both possibilities. Some slow slip events appear to reduce seismicity in the months and years following the event. Some slow slip events are followed by increased seismicity, and a few slow slip events have been followed by large, damaging earthquakes. The overall statistical relationship is unclear. Slow slip events are common, large earthquakes are rare. The probability that any individual slow slip event leads to a large earthquake is low, but the probability is not zero. The second question is how much stress a slow slip event can transfer to a locked fault segment before that segment fails. This is a question about thresholds. Locked fault segments can handle a certain amount of additional stress without rupturing, but there's a limit. If the stress exceeds that limit, the fault fails. The problem is that the limit is different for every fault segment, and it's difficult to measure in advance. Some locked segments are close to failure and can be triggered by small stress perturbations. Some locked segments are far from failure and can withstand large stress perturbations without rupturing. On the Hikurangi subduction zone, seismologists don't know exactly how close the locked southern section is to failure. They know it's been accumulating stress for more than 500 years. They know the average recurrence interval is about 500 years, but they don't know whether the next earthquake will occur tomorrow or 100 years from now. The stress threshold is unknowable with current technology. It can only be inferred from models, and models are approximations. The third question is whether there are observable precursors to large subduction earthquakes that scientists haven't recognized yet. The historical record suggests that some large earthquakes are preceded by slow slip events, but not all large earthquakes have that precursor. Some occur without any detectable warning. It's possible that there are other precursors, subtle changes in seismicity patterns, or GPS motion or tremor behavior that occur before large earthquakes but haven't been identified yet. It's possible that the signal is there in the data, buried in the noise, and scientists just haven't learned how to see it yet. Or it's possible that some earthquakes genuinely occur without precursors. The fault goes from locked to ruptured without passing through any intermediate state that's measurable from the surface. The uncertainty is not a failure of science. It's a reflection of the complexity of the system. Subduction zones are vast, three-dimensional structures extending hundreds of kilometers in length and depth. The stress state varies across that structure in ways that are difficult to measure. The material properties of the rock vary. The fluid pressures vary. The frictional properties vary. Predicting when and where a fault will fail requires knowing all of those variables with precision. And current technology doesn't allow that level of precision. What scientists can do is monitor the system. They can track the observable signals, GPS motion, seismicity, tremor. They can watch for changes in those signals that indicate the fault is doing something unusual. And they can communicate those observations to policymakers and the public. But they can't predict earthquakes in the way that weather forecasters predict storms. The physics doesn't allow it, not yet. The fourth question is what role human activity plays in the earthquake cycle. This is a controversial topic, and it's worth addressing directly because it often comes up in discussions of earthquake hazard. In some parts of the world, human activities like wastewater injection, reservoir impoundment, and geothermal energy extraction have been linked to increased seismicity. The mechanism is well understood. Injecting fluids into the crust increases pore pressure, which reduces friction on faults. When friction is reduced, faults can slip more easily. But these human-induced earthquakes are typically small, magnitude 5 or less. They occur in regions where human activities have directly altered the subsurface stress state. And they're distinct from the tectonic earthquakes that occur on major plate boundaries. On the Hikurangi subduction zone, there's no evidence that human activity is influencing earthquake occurrence. The stress driving the fault is tectonic, not anthropogenic. The earthquakes are part of the natural earthquake cycle that's been operating for millions of years. Climate change is sometimes raised as a factor. The argument is that changes in sea level or glacial loading could alter the stress state of the crust and influence earthquake timing. The physics is plausible. Large changes in surface loading, like the retreat of ice sheets at the end of the last ice age, do create stress changes in the crust. And those stress changes can influence seismicity over thousands of years. But on the timescales relevant to modern earthquake hazard, decades to centuries, climate-induced stress changes are small compared to the tectonic stresses driving plate convergence. They might alter the timing of earthquakes by years or decades, but they're not the primary driver. The Hikurangi subduction zone is moving because the Pacific plate is converging with the Australian plate. That convergence is driven by plate tectonics, by convection in the Earth's mantle, by processes that operate on geological timescales. Human activity isn't causing the earthquakes, but it does influence the consequences. Building practices, land use decisions, emergency preparedness, all of these human factors determine how many people are killed when an earthquake occurs. A magnitude 8 earthquake in an unpopulated area kills nobody. A magnitude 8 earthquake beneath a major city kills thousands. The earthquake is the same. The human consequences are entirely different. That's why preparedness matters. It's why building codes matter. It's why public education campaigns about tsunami evacuation matter. Scientists can't prevent earthquakes from occurring, but engineers, policymakers, and communities can reduce the consequences when they do. So where does that leave us right now at this specific moment, with 3 earthquakes in the last 24 hours and a fault system that's capable of producing catastrophic events? The honest answer is that we're in a waiting period. The earthquakes have occurred. The data is being collected. The analysis is ongoing. And over the next 72 hours, the pattern will either develop or it won't. If the pattern develops, if additional earthquakes occur in the same region, if GPS stations detect motion, if tremor appears in the seismic record, then scientists will confirm that a slow slip event is underway. That confirmation won't tell you that a large earthquake is coming, but it will tell you that the fault is in motion. It will tell you that stress is being transferred, and it will update the probability calculation if the pattern doesn't develop, if the seismicity tapers off, if the GPS stations show no anomalous motion. Then today's earthquakes were probably isolated events. The system returns to normal. The monitoring continues. And the next event, whenever it occurs, will be a new story. The challenge for anyone watching this unfold is the uncertainty. You want a clear answer. You want to know whether this is dangerous or not. And the science can't give you that answer yet. What the science can tell you is what to watch for. Here are the signals that would indicate a developing slow slip event. First, additional earthquakes in the same region over the next 48 to 72 hours. Not just 1 or 2, a sustained sequence. The earthquakes should cluster geographically, forming a pattern that suggests a region of the fault is under stress. Second, GPS motion. Stations near the epicenter locations should begin showing displacement over the next 24 to 72 hours. The motion should be in a direction consistent with the plate boundary slipping beneath the North Island. The displacement will be small, a few millimeters initially, but it should be measurable and sustained. Third, tremor. Seismologists monitoring the deep seismic signals should detect low-frequency vibrations consistent with tremor. The tremor should occur at depths of 30 to 40 kilometers, marking the down-dip edge of the slipping region. If all 3 signals appear, scientists will know they're watching a slow slip event in real time. If only 1 or 2 signals appear, the interpretation becomes more ambiguous. And if none of the signals appear, today's earthquakes were probably just background seismicity. The data collection is continuous. GPS stations update every few hours. Seismometers record continuously. The analysis teams at GNS Science are watching the data streams in real time. If something significant develops, they'll see it almost immediately. Public communication of those developments is more complicated. Scientists are cautious about raising alarms based on preliminary data. False alarms erode public trust. Overwarning creates complacency. The threshold for public communication is high. If a slow slip event is confirmed, and if that event shows signs of propagating toward the locked southern section, authorities will consider whether to issue public information updates. But those updates won't be earthquake predictions. They'll be statements of fact about what the monitoring data shows. For the general public, the message is the same whether a slow slip event is happening or not. If you live on the east coast of the North Island, you should already know your tsunami evacuation route. You should already have emergency supplies. You should already know the natural warning signs of a tsunami. A slow slip event doesn't change those fundamentals. It just updates the probability that you might need to use that knowledge in the near term. For scientists, The next 72 hours are critical. This is the window when a slow slip event, if it's happening, will become obvious in the data. This is when the pattern will emerge. And if the pattern does emerge, the monitoring shifts from passive observation to active tracking. The question changes from, is this a slow slip event, to, how large is it, how fast is it moving, and where is it going? Those questions have concrete answers. They can be measured, they can be tracked, and they provide information that informs preparedness. But the fundamental uncertainty remains. Even if a large slow slip event is confirmed, even if it propagates toward the locked southern section, even if it transfers significant stress to that locked region, there's no way to predict whether the fault will rupture. Most of the time, it won't. The fault will absorb the additional stress. The slow slip event will taper off. The system will reset, and nothing catastrophic will occur. But sometimes, maybe one time in 10, maybe one time in 20, the additional stress is enough. The fault reaches its threshold, and it fails. That's the scenario that seismologists are watching for, not because they expect it, but because the consequences are large enough that even a small probability demands attention. Part 15. Why? This matters beyond New Zealand. The Hikurangi subduction zone is not just a New Zealand problem. It's a natural laboratory for understanding how subduction zones work worldwide, and the lessons being learned here have implications for earthquake hazard everywhere that tectonic plates converge. Slow slip events were first discovered 24 years ago. Before 2002, seismologists didn't know they existed. The entire phenomenon was unknown. Now, slow slip events have been documented on subduction zones around the world. Japan, Mexico, Alaska, Chile, the Pacific Northwest. Wherever dense GPS networks have been deployed on subduction zones, slow slip events have been found. That suggests slow slip is a fundamental feature of how subduction zones work, not an anomaly specific to one or two locations. It suggests that the traditional model of subduction zones, where the fault is either locked or slipping into earthquakes, was incomplete. The new model includes a third mode, slow slip, and understanding that mode is critical to understanding earthquake hazard. The Hikurangi subduction zone is particularly valuable for research because the slow slip events occur at unusually shallow depths. In most subduction zones, slow slip occurs at depths of 30 to 60 kilometers, too deep to instrument effectively with ocean bottom sensors. But at Hikurangi, slow slip occurs as shallow as 2 to 5 kilometers below the seafloor. That shallow depth makes it possible to deploy instruments directly at the plate boundary. It makes it possible to record slow slip events in unprecedented detail. And the data collected from those instruments is being used to refine models of subduction zone behavior worldwide. The seamount connection, the discovery that subducted seamounts control where slow slip occurs, is another result with global implications. Seamounts are common on subducting oceanic plates. They're features that can be mapped, and if seamounts control slow slip, then the distribution of slow slip events on subduction zones worldwide might be predictable from the distribution of seamounts. That's a testable hypothesis. Researchers are working on it right now. They're mapping seamounts on subducting plates in Japan, Alaska, and South America. They're looking for correlations between seamount locations and slow slip locations, and preliminary results suggest the correlation holds. If it does, it means scientists can predict where slow slip events will occur based on the geology of the subducting plate. That's not the same as predicting when they'll occur, but it's a step toward understanding the system. The stress transfer mechanism, The process by which slow slip events load neighboring fault segments is also being studied intensively. If slow slip events can trigger large earthquakes, understanding the conditions under which that happens is critical for earthquake hazard assessment. The Hikurangi subduction zone has provided natural experiments like the Kaikoura earthquake and the triggered slow slip events that are advancing that understanding. The data collected from those events is being used to refine models of stress transfer and fault interaction. Those models are then applied to other subduction zones. The Cascadia subduction zone in the Pacific Northwest, which runs from Northern California to southern British Columbia, is one of the most studied. Like Hikurangi, Cascadia produces slow slip events. Like Hikurangi, Cascadia has sections that are locked and accumulating stress. And like Hikurangi, Cascadia is capable of producing magnitude 9 earthquakes. The last major earthquake on Cascadia was in 1700. The geological evidence suggests it was magnitude 9 or larger. The tsunami crossed the Pacific Ocean and was recorded in Japan. The earthquake itself is known only from Native American oral histories, tsunami records in Japan, and geological evidence of coastal subsidence and tsunami deposits. The next Cascadia earthquake, whenever it occurs, will affect millions of people in Seattle, Portland, and Vancouver. Understanding how Cascadia works, including how slow slip events interact with the locked sections of the fault, is a matter of national importance for both the United States and Canada. Research on the Hikurangi subduction zone contributes directly to that understanding. The physical processes are similar. The fault geometry is similar. The lessons learned in New Zealand apply to Cascadia and to every other subduction zone where slow slip occurs. That's why today's earthquake swarm matters beyond New Zealand. It's a data point. It's another example of how subduction zones behave, and every example adds to the growing body of knowledge about these systems. The ultimate goal is to understand subduction zones well enough to assess earthquake hazard accurately. Not to predict individual earthquakes, but to know which fault segments are most likely to rupture, on what timescales, and with what consequences. That knowledge allows for better building codes, better land use planning, better emergency preparedness. It allows communities to make informed decisions about risk. The science is not there yet. The understanding is incomplete, but it's improving. Every slow slip event that gets recorded, every earthquake swarm that gets analyzed, every GPS station that detects motion contributes to the progress. And today, right now, with 3 earthquakes in the last 24 hours on the Hikurangi subduction zone, the progress continues. Part 16. The uncomfortable truth. Here's the truth that seismologists live with every day. The truth that makes conversations about earthquake hazard so difficult to communicate to the public. Most of the time, earthquake swarms are just noise. They're background seismicity. They're the Earth's crust adjusting to stress in ways that are normal and harmless. But sometimes, rarely, they're not. Sometimes an earthquake swarm is the leading edge of something larger. Sometimes it's a slow slip event that propagates. Sometimes it's a precursor to a major rupture. And sometimes, very rarely, it's the foreshock sequence before a magnitude 8 or 9 earthquake that kills tens of thousands of people. The challenge is that the signals look the same. 3 magnitude, 4 to 5 earthquakes in 24 hours could be nothing, or it could be something. The data doesn't tell you which it is until days or weeks later, when the pattern either develops or it doesn't. This creates a communication problem. If scientists issue warnings every time there's an earthquake swarm, the false alarm rate is enormous. People stop paying attention. Public trust erodes. And when a real warning is issued, nobody listens. But if scientists stay silent, waiting for certainty before communicating, they risk being caught off guard when a swarm turns into something larger. The solution that's evolved in New Zealand and in other earthquake-prone regions is to communicate the process rather than the outcome. Scientists don't issue predictions. They explain what's being observed, what it might mean, and what people should do to prepare. That's what this video is doing. It's explaining what 3 earthquakes off the coast of New Zealand might mean, given what we know about the Hikurangi subduction zone. It's not predicting a disaster, it's providing context. The uncomfortable truth is that the outcome is genuinely uncertain. The earthquakes could be nothing, or they could be the start of a slow slip event, or very rarely, they could be the precursor to a magnitude 8 earthquake. The probabilities favor nothing. Most earthquake swarms are just noise, but the consequences of the rare events are large enough that even small probabilities demand attention. That's the logic behind earthquake monitoring. It's not that scientists expect a major earthquake to follow every swarm. It's that the consequences of missing the signal are so large that the monitoring has to be continuous, comprehensive, and communicated clearly. The other uncomfortable truth is that preparedness is not optional. Whether today's earthquakes are significant or not, whether a slow slip event develops or not, whether a major earthquake occurs this year or in 100 years, the hazard exists. The Hikurangi subduction zone will rupture again. That's not a prediction. It's a statement of geological fact. The fault has ruptured repeatedly over thousands of years. The stress is accumulating. The next earthquake is coming. The only questions are when and how prepared people will be when it happens. New Zealand has made significant investments in preparedness. Building codes have been updated. Tsunami evacuation zones have been mapped. Public education campaigns have been conducted. Emergency management agencies have response plans, but preparedness is not a one-time effort. It requires sustained attention, sustained funding, and sustained public engagement. It requires people to know their evacuation routes, to have emergency supplies, to understand the natural warning signs of tsunamis. And it requires accepting that uncertainty is part of living on a tectonic plate boundary. You can't eliminate the hazard. You can only prepare for it. If you live on the east coast of New Zealand's North Island, the message from today's earthquake swarm is simple. It's the same message that's been communicated for years through public safety campaigns, and it doesn't change whether this swarm is significant or not. Know your tsunami evacuation route. If you haven't identified it yet, do it now. Tsunami evacuation zones are mapped for every coastal community. The maps are available online through local civil defense organizations and often posted in public places. Know the natural warning signs of a tsunami. If you feel a strong earthquake, or if you feel a weak earthquake that lasts more than a minute, and you're near the coast, move immediately to higher ground or as far inland as you can. Don't wait for an official warning. The earthquake is the warning. Don't return to the evacuation zone until authorities confirm it's safe. Tsunamis arrive in multiple waves. The first wave is often not the largest. The danger period can last for hours. Have an emergency kit: water, non-perishable food, flashlight, radio, first aid supplies, important documents. Enough to sustain yourself and your family for at least 3 days without external support. Know how to turn off utilities. Gas, water, electricity. If a major earthquake occurs, there's a risk of fires, floods, and electrical hazards. Knowing how to shut off utilities can prevent secondary disasters. Have a communication plan. After a major earthquake, cell phone networks may be overloaded or damaged. Identify an out-of-region contact that family members can call to check in. Text messages often go through when voice calls don't. These are the basics of earthquake and tsunami preparedness. They apply whether you live in New Zealand, Japan, Chile, Alaska, or anywhere else on a tectonic plate boundary. The specific relevance to today's earthquake swarm is this. If the GPS data over the next several days confirms that a slow slip event is underway, it's a reminder that the fault is active. It's a reminder that the hazard is real. And it's a reminder that preparedness is not something you do once and forget. It's something you maintain. But even if today's earthquakes are just background seismicity, even if no slow slip event develops, the fundamentals don't change. The Hikurangi subduction zone is capable of magnitude 8 or 9 earthquakes. Those earthquakes will generate tsunamis, and those tsunamis will arrive in minutes. The time to prepare is not after you feel the earthquake. It's now, before anything happens. When you have time to think clearly, to make plans to gather supplies, that's not fear-mongering. It's just the reality of living on a planet where tectonic plates move, faults fail, and earthquakes happen. Part 18. The question science can't answer. The question everyone wants answered is the one question science can't answer. When will the next major earthquake occur? People want a date. They want a timeline. They want to know whether they should be worried this week, this month, this year, or whether they can relax for a decade or two. Seismology can't provide that answer. Not now, maybe not ever. The Earth's crust is too complex, the variables are too numerous, and the measurements are too imprecise. Scientists can tell you that stress is accumulating. They can tell you that the probability of an earthquake increases over time. They can tell you which fault segments are most likely to rupture, but they can't tell you when. The best available estimates are probabilistic, a 26% chance of a magnitude 8 or larger earthquake on the southern Hikurangi subduction zone over the next 50 years. That's not a prediction. It's a statement about probability. It means that if you could run the next 50 years 100 times, you'd expect a magnitude 8 or larger earthquake in about 26 of those scenarios. But in any individual timeline, in the one we're actually living in, the earthquake either happens or it doesn't, and the probability estimate doesn't tell you which outcome you're in. This frustrates people. It's understandable. Humans want certainty. We want to know what's coming. We want to plan. But uncertainty is fundamental to the system. Earthquakes are threshold phenomena. They occur when stress exceeds strength. The exact moment when that threshold is crossed depends on variables that can't be measured in advance. Scientists are working to improve earthquake forecasting. They're studying slow slip events as potential precursors. They're deploying denser networks of instruments. They're developing better models of fault behavior. Progress is being made, but it's incremental, and it may never reach the level of precision that would allow for deterministic predictions. The question that science can answer is what to do about the uncertainty. And the answer is prepare. Build resilient infrastructure. Educate the public. Maintain emergency response capabilities. Accept that earthquakes will happen, that they can't be prevented, and that the best response is to minimize the consequences when they do. That's not a satisfying answer for people who want to know when the next earthquake will strike, but it's the honest answer. And it's the answer that saves lives. Part 19. What happens next? Over the next 72 hours, the GPS data will either show motion or it won't. Additional earthquakes will either occur or they won't. The pattern will either develop or it won't. Scientists are watching. The data is being collected. The analysis is ongoing. If a slow slip event is confirmed, you'll see updates from GNS Science and GeoNet. The scientific community will communicate what's being observed. Civil defense authorities will consider whether public information updates are warranted. If no slow slip event develops, the earthquake swarm will be cataloged as a routine seismic sequence. The monitoring will continue, and the next event, whenever it occurs, will be analyzed on its own merits. Either way, the Hikurangi subduction zone continues to move. The Pacific plate continues to subduct beneath the Australian plate. The stress continues to accumulate, and somewhere, at some depth, on some fault segment, the next earthquake is waiting. It might wait another 100 years. It might happen tomorrow. The data doesn't tell us which. What the data does tell us is that the system is active, that the hazard is real, and that preparedness is the only rational response to living on a tectonic plate boundary. 3 earthquakes in 24 hours, all shallow, all in the same location, all sitting directly above one of the most dangerous fault systems in the world. That's where we are. This is Project Nightfall Watch. The ground moved, the data is being collected, and the next 72 hours will tell us whether this is the beginning of something larger or just another day in the life of a subduction zone. Stay with us for updates as this story develops, because when the Earth starts speaking, the only responsible thing to do is listen.